So next we're going to look at the relationship between different root indexes and powers inside of those roots and something called fractional or rational exponents. So the general form is if you have a radical expression, say for example, just the square root of a and then b to the c power, um, this value right here is the numerator of my rational exponent, and this value is my denominator. So I could rewrite this as this is equivalent to b raised to the c over a power. So you can see that's not the number 9. I have a fractional or rational exponent, right? And this is a. The numerator is the value c, that was the exponent inside of the radical, and the denominator of that is a root index, and this was a. And the base is the same, right? The base of this was b. You can see the base here is still b. So if I look at that makes these pretty straightforward. This expression would be the same as x raised to the 5/3 power. And the other one would be x raised to the 7/4 power. Now, because of that relationship, um, I mean, you could rewrite these. I don't know why you would, but this is the same as 64 squared, and then the third root of that. But our calculators do a pretty good job of evaluating these expressions as is. So I'll go ahead and clear this. I'm going to just take 64 and raise it to the power of, and then up in my exponent I'm going to write 2 divided by 3. And when I do that, I get exactly the number 16, so this is equivalent to 16. The next one, I've got the square root of 36 cubed. I'm just playing with it in my mind. The square root of 36 is 6. And I don't know what 6 cubed is, so let's look at this. 36 raised to the power of 3 to the second power. Yeah, and that should be 6 to the third power. It should be the same as that. And it is. It's 216. So this is 216. And then our final example here is 125 to the 5/3 power. So 125. I think the cubed root of 125 is 5. So this should be 5 to the third raised to the 5 divided by 3 power. And that's 3,125. 3,125. Couple expressions here that make sure they're in your notes. One of them is the area of a circle, and the other is the circumference of a circle. It was kind of cool when we looked in class where these came from. We were considering regular polygons with more and more and more sides. And we saw that as we increase the number of sides, the area approaches this expression, pi r squared. So the area of a circle is pi times the radius squared, and the circumference is 2 times pi times the radius, or alternately, if you know the diameter, it's just pi times the diameter, which is not a mystery because if you double the diameter, the radius, you do get the diameter. So that's all that's talking about. So for this problem here, right, we've just got pi times, the area is pi times this 2.4, and we will square that. And I'm fine with you leaving that as the answer. However, if it's a multiple choice test, you would have to look at this. So I think this is the pi. No, that's the e. I'm embarrassed to say that I literally cannot see where pi is on this. Oh, it's the exponent one. So there's pi, and I'll just take that times 2.4 to the second power. So order of operations, it is going to square the 2.4 first, and then multiply that by a decimal equivalent of pi. So we're looking at an area of about 18.1 if I was rounding to the nearest tenth. So I'd say area is approximately 18.1. And the next, oh, we're also asked to find the diameter, right? The diameter would be 2 times pi times the radius, so 2 times, here is pi again, and then times this radius of, what was it, 2.4. So it looks like about 15.1. So the circumference is 15.1. And then, terrible mistake, right? I should include units. So circumference is 15.1 inches. The area is 18.1 inches squared, right? This is an area, so we're talking about square units. For 26, the radius of this is 13, so the area is pi times 13 squared, and the circumference, I'll just write as pi times 26, pi times the diameter. So if I was to find decimal equivalents for each of these, right, this is approximately, so I'm looking at pi times 13 squared. That is not squared. I'm sorry. Pi times 13 to the, I'll just do to the second power. So it's about 530.9. And the other one's pi times 26, so second pi times 26. And that's about 81.7. And I've done it twice now, so units matter, right? These are square centimeters, and these are just centimeters. Next, we're asked to find the area of a sector of a circle, and we looked at two things. We looked at arc length and areas of sectors. Again, this is not the entire circle, right? We don't have the whole circle here. We just have a small part of it. This central angle is 360 degrees if I went all the way around. And you can see that we have 45 out of a possible 360 degrees. So that's the fractional part of the circle that we have. So all we do is we identify the part of the circle we have, and then we just multiply that by the area of the entire circle, which would be pi times 2 yards squared, or 4 pi. So again, it's not the whole circle, it's just this part of the circle. So our area, if we evaluate that expression, we're looking at 45 divided by 360, and I'm going to multiply that times pi, and then times 2 to the second power, 4. And when I do that, I clearly made an error. Oh, I see, I didn't get pi. Let's see, second pi. There we go. No, still didn't get pi. Second pi. There it is. So 45 out of 360 degrees times pi times 2 squared. So that gives us an area of approximately 1.6. I should write approximately. About 1.6. And if you kind of think about it, I know some of you were kind of surprised, like, wow, that seems really small. These are square yards. Remember, the area of this whole thing would be 4 times pi, right? So, and if I'm looking at 4 times 3 very roughly, I'm at about 12. Well, if I take half of that, right, in other words, if my angle was 180 degrees, that would give me about 6. And if I take half of that 6, that would give me 3. And if I take half of that 3, I'm looking at about 1.5. So yeah, this checks out with kind of a rough look at it approximation. I would expect it to be around 1 point, a little bit bigger than 1.5. And why is that? Because it's not a half, it's not a quarter, it's about 1/8 of the circle. So the area is about 1.6 square yards. The last two problems here, we've got some we've got an absolute value function, and we have a quadratic function that's written in graphing form. For this first one, if you just consider a table of values, you could plug some things into it and see what's happening with it. When I take -10, actually let's look at this as a table of values. So let's see, here's our x's, here's our y's, and this y is the absolute value of x plus 2 minus 5. So when I put -10 into this function, -10 plus 2 is -8. The square root of the absolute value of -8 is 8, and 8 minus 5 is 3. I could do the same thing for 9. -9 plus 2 is -7. Absolute value of that is 7. 7 minus 5 is 2. -8 produces the somewhat predictable result of 1. That's -6. Absolute value, which is 6 minus 5 is 1. If I put in -7, this is interesting. -7 plus 2 is -5, absolute value, which is 5. And 5 minus 5 is 0. So I see this pattern going on, right? There's the -10. Oops, I'm sorry. The -10 goes to a +3. The -9 goes to a +2. The -1 goes to a +0, or to the -8 rather goes to 0. No, the -8 goes to 1. It is the -7 that goes to 0. And I just continue in this fashion. However, this is an absolute value function, and everything changes at a particular spot. Where is that spot? Well, just like our parabola in graphing form, it ends up being at -2 on -5. So, if we're focusing on these, this kind of models what happened, or it parallels what happens with our quadratics in graphing form. The vertex of this, or the spot where it changes directions, happens at -2, -5, this spot right here. And beyond that, it's just these two linear functions. So I just keep connecting these dots, dot, dot, and then it changes, and then it has the same slope going out. So dot, 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 dot. So it ends up being just this this shape, this V. And if you want to look at these on your graphing calculator, one of the things you can do is use this ABS function. I'll show you how you get to it. If you press math and go over to num, it has the absolute value function. So from there you can enter the absolute value of x plus 2. You can see I closed my parentheses and then subtracted 5 from that. So let me clear that. And when you graph it, you see precisely the thing that we're seeing on our paper here. The other thing, if I look at this, this is going to have its vertex at when x is +1, so that's my axis of symmetry. Oh no, I'm sorry. Actually, no, it's going to happen when x is -3. So here is my axis of symmetry. And the y value at that point is going to be +1. So this is a parabola because it is opening upwards, right? It does not have a it won't have roots at all. It's just hovering above it, and it's just going to go this direction. And I got to be careful. It's y-intercept is rather large. And you can see this, if x is the number 0, I could evaluate it. 3 squared is 9, double that's 18, 18 plus 1 is 19. So the y-axis, y-intercept ends up happening, the y-intercept ends up happening when, what happens when x is 0, but y would equal 19 at that point.